Hey there, in this video we're going to look at some more applications of linear first order differential equations. We're going to start out with free falling bodies. So usually this is an object falling from the sky. And we're going to restrict ourselves to just looking at two forces acting on that body. Here you can see a free body diagram of this. I've got the gravitational force pushing down on our object, and then the resistance of air that it's flowing through is pushing back against that. We're going to have that downward force be in a positive direction, which makes the air resistance be in a negative direction. So we'll see a negative on that air resistance here. And then the net force, the overall force acting on this body, is just going to be the sum of those two forces, the gravitational and resistance forces. So gravitational force, that's going to be mass times gravity. And make sure that you're using the right constant for gravity, depending on the units that you're working with in a particular problem. And for air resistance, we've got the negative on there to represent that opposing direction from gravity. And it's just going to be a proportionality constant K times V, the velocity, which V is going to be a variable with respect to time. So we can call that V of t. And if I just add up these forces, I get the total force of the model here. So mg minus kv is equal to that total force. And the total force is also equal to mass times acceleration. So I get the differential equation mass times dv dt equals mg minus kv. Okay, so that acceleration is the derivative of the velocity. So now I have a function in terms of a differential equation in terms of v. The solution of this equation would be v of t. So there's a lot of letters in here, but the m, g, and k, those are all constants. Those are values that we want to be plugging in, and v and t are our variables. And just as a side note, if I find that solution v of t and I integrate it, then I will get the position function that describes the position of the object at any particular time. Here I'm calling it x of t. We might see it called displacement function or s of t, depending on where you're looking. Okay, so let's look at an example of this. So a 400-pound object is released from rest 500 feet above the ground and allowed to fall under the influence of gravity. Assuming that the force in pounds due to air resistance is negative 10 v, where v is the velocity of the object in feet per second, we want to determine the velocity equation of the object. So we're going to set up a differential equation and solve it to find v. So first thing I always do with a word problem, so I usually have to read it a couple times, and that second time I read through, I start pulling out the information that was given to me. So I have that 400 pounds is the first thing that jumps out at me. That's pounds, which is not a mass, it's a weight or force. So my first force is 400 pounds. Okay, so be careful with that when you're dealing with the US system and they give it to you in pounds, they're giving you the whole force, not just the mass. And then we've got the second force, the air resistance, which is that negative 10 v that I was given. I'm also going to need gravity, and since I was given pounds and we're dealing in feet per second, we're in the US system, I'm going to use 32 feet per second squared. And then they also said that this is released from rest, so that means my initial velocity is 0, so v of 0 equals 0. Okay, so I need the mass for my formula, so I am going to take that 400 pounds and I'm going to solve it for m. Okay, so for the force is equal to mass times gravity, so 400 is going to be equal to 32 times m. Dividing it by 32, I get 12.5, and we're not going to focus too much on units in this class, but it is slugs in the US system. So 12.5 slugs is what we've got for the mass. So now from all of this, I have everything I need to plug in to our formula. M times dv dt equals mg minus kv. So that 12.5 goes out on the left, and then we got the 400 minus 10v on the right. And so this is a linear first order differential equation. I have a couple options here. I could solve this using separation of variables, or I can solve it using integrating factor. I went ahead and picked separation of variables for this first example, but you could use an integrating factor if you prefer here. Okay, so to separate the variables, I'm going to divide by 12.5. So dv dt equals 32 minus 0.8v. And then I'm going to divide by that whole right side, and multiply by dt to separate the variables. So dv over 32 minus 0.8v equals dt. And then I can integrate both sides of this equation. That left side does require a u substitution. So u is going to be the entire denominator, 32 minus 0.8v, which means du is equal to negative 0.8. Or if I divide that negative 0.8 over to the left side, so I can just swap it out, dt is going to be equal to negative 1.25 du. So I end up with an integral of negative 1.25 times the integral of du over u equals to our integral of dt, and I'm ready to integrate both sides of this equation. 1 over u is just natural log of absolute value of u, so negative 1.25 times the natural log of u equals t plus our constant of integration. So this c1 is accounting for both constants for both integrals that we integrated, and just throw it on the right side. And it is going to change, so I'm calling it c1. So as I start folding more values into it, it changes with each step. Okay, so I need to plug my v back in place of the u, and I'm going to divide by the negative 1.25. Okay, so I end up with natural log of absolute value of 32 minus 0.8v on the left, and negative 0.8t plus c2 now on the right side. Okay, so I changed the name of the constant because I divided it by negative 1.25. Okay, so now I'm going to exponentiate both sides of this equation. So I have an e to each of these. And I'm also going to take care of the absolute value by throwing a plus or minus on the right side. So 32 minus 0.8v equals plus or minus e to that whole quantity, negative 0.8t plus c2. Now, before I go any further, I'm going to clean that up a little bit. I can split up that exponent so that I have e to the negative 0.8t times e to the c2. And then I can just rename that and fold in the plus or minus as well. So it makes things look much nicer. 32 minus 0.8v equals c3 e to the negative 0.8t. Okay, so we're almost there. Just got to get rid of the 32 and the negative 0.8, and we will have a function for v. Okay, so I'll subtract 32 from both sides and then divide by negative 0.8. Okay, again, folding everything to the constant, and that's the last time the constant is changing, so I'm just going to call it c. So I get the function v of t equals c times e to the negative 0.8t plus 40. And they did have, remember we had those initial conditions that the initial velocity is 0. So I can use that to solve for c. Okay, so plugging in 0 for v of t and for t, I get 0 equals c e to the 0 plus 40. And so that means that c is going to equal negative 40 if I just subtract the negative 40, or subtract the 40 over. And I get a final function, v of t equals 40 minus 40e to the negative 0.8t. Okay, so that's what it looks like to solve a free-falling body model. We're going to do one more example with a different application. We're going to look at some series circuits. Now, we're not going to get deep into this. If you take a physics class, you will spend a lot more time with this topic. For us, we just want to kind of see how differential equations can come up in a circuit. So I've got two types of circuits that we'll look at. An LR circuit, which the L is going to stand for inductor, and the resistor is R. Or an RC circuit where I have a resistor and a capacitor. So these are both coming from Kirchhoff's law, and I do have an image on the left. Usually that energy source is going to be either a circle or it'll be those double lines that are two different lengths to indicate that. So if you run into examples where you see either one of those symbols, you're talking about your voltage source or your E of t. Okay, so for an LR circuit, we have this relationship L times di dt, where I is the current, plus the resistance times the current equals E of t. Right? A nice linear first order differential equation that we can solve if we've got all the values to plug in. For an RC circuit, the resistance times dq dt, which is going to be the derivative of your charge, or the change in charge over time, plus 1 over c, the capacitance, times the charge, equals E of t. Okay, so we'll do one example using one of these formulas, and we'll have more examples in the homework. And just one other thing to note, the relationship between current and charge is that the current I of t is equal to the derivative of the charge dq dt. Okay, for our second example, a 200 volt electromotive force is applied to an RC series circuit in which the resistance is 1000 ohms and the capacitance is 5 times 10 to the negative 6 farad. Find the charge Q of t on the capacitor if I of 0 equals 0.4. Determine the charge and current at time equals 0.005 seconds, and determine the charge at t as t approaches infinity. So a lot of things they're asking for here. We got 3 things we're going to find. First off, I've got to take all these values they gave me, label them with the appropriate variables so that I can set up my differential equation. Okay, so they told me the resistance is 1000 ohms. Capacitance is 5 times 10 to the negative 6 farad. That voltage that they gave us, that's your E of t. So 200 volts is E, and it's constant here, so it made things a little simpler. And they gave us that initial condition that I of 0 equals 0.4. Okay, so with all this information, we can use one of those formulas. So R dq dt plus 1 over c times q equals E of t. And we can plug all this in to get our differential equation. So 1000 dq dt plus 1 over 5 times 10 to the negative 6 times q equals 200. So plugging that in makes it a little easier to see what we're looking for here. I'm going to solve this differential equation for q of t, and that'll give me the first thing they asked for, the charge. Okay, so it's another linear first order differential equation. We did separation of variables on the last one, so I'm going to use an integrating factor this time just to switch it up. So if you're going to use an integrating factor, first thing we have to do is put this in standard form, which means I can't have that 1000 multiplying by dq dt. So I got to multiply everything or divide everything by the 1000 to clean this up, and I get dq dt plus 200q equals 0.2. Okay, it's in standard form now, so now I can find my integrating factor mu. Okay, so p of t is going to be 200. Integrating that gives me 200t. And then my integrating factor will be e to the 200t. Okay, so to use that integrating factor, I'm going to multiply everything in the equation by e to the 200t. And it looks like this now. E to the 200t plus dq dt times dq dt plus 200 e to the 200t times q equals 0.2 e to the 200t. Okay, so if I found my integrating factor correctly, the left side should be the derivative of e to the 200t times q. And you can check that by just doing a quick product rule, and you should get what we had in the previous step. And then I can integrate this on both sides to get rid of that derivative. So e to the 200tq is going to be equal to the integral of that 0.2 times e to the 200t on the right. Okay, if I integrate the right side, you might want to do some u substitution for that, but you should get 0.001 e to the 200t plus c for that. And I'm almost there. To solve for q, I just divide both sides of the equation by the e to the 200t. It's going to cancel out the first term and end up with an e to the negative 200t, multiplying by my constant of integration in that second term. Okay, so I found the first thing they asked for, the q of t, although I haven't found the constant of integration yet. They gave me some initial conditions, but those were for I, not for q. And I have to find the charge and the current, so I need to find I of t as well. And so it helps to remember that, there's my initial conditions they gave me, to remember that I of t equals dq dt. So if I just take the derivative of the answer I just got, then I can find I of t. So taking that derivative, well, the 0.001, derivative of that is 0, and derivative of c e to the negative 200t gives me negative 200c e to the negative 200t. And now I can use my initial conditions on this equation, the charge function. So plugging in 0 for t and 0.4 for I of t, we get 0.4 equals negative 200c times e to the 0, or 1. And dividing that, I get a constant of negative 0.002. So this does double duty. I now have the c to plug into both q of t and I of t. So I can plug them into both places, and I get an equation for the charge and for the current. So I've now found the first few things they asked for, found the charge function, found the current. They also want me to find the charge and current at the time 0.005. So that's what we'll do next. And that's just taking our two equations that we just got and plugging in that time. So I'll take Q of t equals 0.001 minus 0.002 e to the negative 200t, and just plug in 0.005 for t. And I get 0.003 coulombs. Again, I'm not going to emphasize the units a lot in this class because it's not a physics class, but you would get a charge in coulombs here. And then I do the same thing for the charge function, and I'm going to get an answer in amps. So plugging in the 0.005 seconds to this equation, we get 0.1472 amps. Okay, and the last thing they ask for is what is the charge as t approaches infinity? And so this is the kind of thing we might be thinking about. Well, if I just take this circuit and I just turn it on and let it run, what happens to the charge over a long period of time? And so taking the limit as t approaches infinity will give us that answer. And that e to the negative 200t is going to approach 0. So we get just 0.001 coulombs for that limit. All right, and that's how you do a problem with a circuit in it. I've got one more formula to give you. I'm not going to do an example in this video, but compound interest is another one where we can write a differential equation. If I have continuously compounded interest, where I'm either depositing or withdrawing a set amount every year, then I get this differential equation, which is another first order linear differential equation. So A is, oh, there's a typo there, is the value of the investment at time t. And so my solution to this differential equation is A of t. R is the interest rate compounded continually, the annual interest rate. And K is however much you're depositing or withdrawing. So you'd have a positive K value if you're depositing money into the account every year, and it would be a negative value if you're withdrawing the same amount every year. So it's just another example. We'd solve it the same way that we solved the last two, either with separation variables or an integrating factor, once you plug in all the values in the appropriate place.